So up until this point, we've been dealing with the interactions between charges on a purely conceptual level. What we're going to start doing now is we're going to start actually calculating the amount of force that two charges exert on each other. And this is going to be very, very similar to the force that two masses exert on each other, which we studied earlier when we did universal gravitation. There are actually a lot of similarities between electric forces and gravitational forces. The main difference that you're going to see, obviously, is we're dealing with charges now instead of masses. And the other main difference is that electric forces can be either repulsive or attractive, whereas the force of gravity is obviously just attractive. So Coulombs law is going to be how we're going to go ahead and calculate the amount of force between two charged objects. And we'll look at what that actually looks like, what that equation looks like on the next page. But for now, let's talk for a second about what that force depends on. So the first thing that it depends on is the charge, okay? Each charge actually matters, just like each mass mattered when we were calculating the force of gravity. And we're going to find that just like gravity, as mass increased, the force increased. With Coulombs law, as charge increases, the force is also going to increase, and that makes sense. The other thing that's going to affect the amount of force is the distance between the charges, just like with gravity. Further apart masses have a lesser gravitational force, and we're going to find that when charges are further apart, their electric force between them is also going to decrease. In equation form here, this is Coulombs law. Fe, the electric force, is equal to K, which is some constant, 9 times 10 to the 9th, just like we had a constant for gravity, times Q1 times Q2, the two charges, divided by r squared, okay, the distance between them. Two important points to make here. Number one, Q1 and Q2 are the magnitude of the charges. So when we're dealing with electric forces, we obviously can have either positive charges or negative charges. When we go ahead and calculate that force, we're just going to take the magnitude of the charge, and we're going to use that positive negative to determine the direction of the force. So we'll worry about that separately. Okay. The second thing is that this is another inverse square law. We see it's divided by r squared. So the force is proportional to the inverse of the distance between the charges squared. Okay, if we double the distance, the force decreases by a factor of 4. And we'll do a few refresher problems with that, just like we did with the universal law of gravitation. Two quick notes here about Coulombs law. The first is, for Coulombs law, the charge must be in coulombs. Okay, sometimes we can be given a charge in E, that fundamental charge, 1.6 times 10 to the negative 19th coulombs, and we'll just have to convert it. The other thing is, and we mentioned this on the last slide, but we're going to use the sign of the charge to determine the direction of the force. So we're going to be thinking about, this charge is positive, this charge is negative, they're attracted to each other, so that's the direction that the forces go. So we'll use that sign to determine the direction of the force. However, in the equation, we're only going to worry about the magnitude of the charge. Okay, the equation is going to just tell us how much force. We'll have to determine the direction separately. Let's go ahead and try a practice problem here with this. So for this one, we want to calculate the electric force between a proton and an electron in a hydrogen atom. We know the distance between them is this 5.3 times 10 to the negative 11th meters. And so we can go ahead and calculate that force using Coulombs law. So the first thing we do is we can plug in that constant there, K, which is just going to be 9 times 10 to the 9th. All right. Charge 1 is the charge of one of the objects. We see here that it's either 1e or negative 1e. So we know we need to get that e into coulombs, and we keep in mind that 1e is just 1.6 times 10 to the negative 19th coulombs. So that's going to be charge 1. Charge 2 is going to be the same thing because they both have a charge of e. Notice I'm not including my negative sign at all here for the electron. In this equation, we only put in the magnitude of the charge, and we're going to ignore whether it's positive or negative, and we'll deal with that separately. We then divide by that distance, 5.3 times 10 to the negative 11th squared, and we end up getting a force here of 8.2 times 10 to the negative 8th newtons. Just for comparison's sake, let's go ahead and calculate the force of gravity that exists between these two objects. So we're going back to the universal law of gravitation, and so we're going to have our big G, 6.67, times our two masses, and that's going to be divided by the distance between them, which from the previous slide was 5.3 times 10 to the negative 11th meters. And we end up finding that the force of gravity that exists between this proton and this electron is going to be equal to 3.6 times 10 to the negative 47th newtons. So let's take a look at how those two forces compare. Our electric force there was 8.2 times 10 to the negative 8th newtons. Our gravitational force was many orders of magnitude smaller, 3.6 times 10 to the negative 47th newtons. And if we're looking at that difference there, that's a difference of about 10 to the 39th. Okay, that is a massive difference between them, 39 orders of magnitude different. And so we see that Fe is a much stronger force. Okay. One way you can really understand this is if you think about those two constants. G is 6.67 times 10 to the negative 11th, whereas that K is 9 times 10 to the positive 9th. Okay, that's one major difference between the two. Another way to understand the difference, though, is think right now, if you're standing on a floor, what is actually preventing you from falling through the floor? And I know that sounds like a ridiculous question, but we have a force of gravity that results from all of the mass on Earth pulling down on us, pulling us towards the center of the Earth. What actually stops us from falling through the floor? And you might say the normal force, and that's true, okay? But where does that force really come from? Okay, if you think about it, the normal force actually comes from electric forces. You have atoms and molecules in your feet, and there are atoms and molecules in the floor. And what ends up happening is those atoms and molecules interact. There's a repulsive force between them, okay? And so you end up getting an upward electric force, all right, between the molecules. And that's what ultimately causes the normal force. And that normal force is strong enough, right? Just that electric force between the atoms and molecules in your feet and the atoms and molecules in the floor is strong enough to overcome the gravitational force from the entire mass of Earth. All right. Something else that's kind of crazy to think about is what actually ends up happening is the atoms and molecules in your foot and the atoms and molecules in the floor don't actually touch. You never really touch the floor. What ends up happening is you just get close enough to the floor that electric force, which depends on the distance, is strong enough to counteract the force of gravity. But if we want to really get down to the nitty-gritty, it's a microscopic difference, but there is absolutely a gap between your feet and the floor. You are, in the technical sense, levitating just slightly above the floor because of the electric forces between your feet and between the floor. And that's actually something that I think is pretty crazy to think about. On top of that, you've never actually touched anything in your life, okay? We simply get close enough to have a really strong electric force, but actual contact between the atoms and molecules in your body and the atoms and molecules in another object has never ever actually happened. Okay, we just get really close. The force is really strong because the electric force is a very strong force, and we get a reaction from it, but actual contact is something that hasn't ever actually happened. Just a real quick aside, there are 4 fundamental forces that we talk about that exist in nature, and they are the strong, the electromagnetic, the weak force, and gravity. Okay, and all the other forces we've talked about throughout the year really are a combination of one or more of these forces. Okay, but you can see that of them, gravity is the weakest. Electromagnetic is actually the second strongest force. Strong and weak are nuclear forces that we're not really going to get into, but just as a quick side note there. Alright, for this problem here, we know the electric force between two charges, A and B, has a magnitude of F, and we want to know how that force on charge A changes if a variety of things happen. So this is one of those new and original things, so I'm going to first set up my original situation using Coulombs Law, Fe equals K Q1 Q2 over R squared. And so we find that force is just going to be F, and that's going to be equal to K times QA times QB, the two charges, over r squared. So there's my original situation. And now I'm going to look at my new situation. So for A, my new situation is that charge B triples, okay? And so my new force here, which I'll call F prime, is going to be equal to K times QA times 3QB all over r squared. I'm going to factor out that 3, so F prime is really just 3 times KQA QB over r squared. That happened to be my original force here, and so I find that for that first one, my new force is just 3 times my original force, which makes sense because Q and F are directly proportional to each other. Moving on to part B here, what happens now is the distance between them is reduced to half as much. And so my new force here, F prime, is going to be K times QA times QB all over R over 2, that quantity squared. So what I end up getting when I do that math there is KQA QB over R squared over 4. I'm going to multiply top and bottom by 4 to get rid of that double fraction, and so I get 4KQA QB all over R squared. We see once again that this is my original force, and so my answer here is that my new force is going to be 4 times that original. For that last one there, I'm told that the sign of charge B changes, but its magnitude does not. And so when that happens, I find that my force F prime is going to be the exact same thing, because there's nowhere that we ever even thought about the sign of each one. So we're going to find that the force there is just the same as the original. Changing the sign will change the direction of the force, but not the amount of force.